Hello viewers, you are welcome to the fourth part of this video series on the necessary and sufficient conditions for Laplace transform. Thank you once again. So in this video we are going to consider a typical function which is exponential 2t. So using this function we want to check if this function has a Laplace transform. But here we're going to focus more on the concept of exponential order, because that is only one that will guarantee to let us know the interval of domain x, or perhaps let me say it this way, the interval of x which the Laplace transform exists. Okay, as we've seen earlier in some videos, in other videos, that the exponential order, it is actually from 0. That exponential order gamma, it actually equals to 0, or perhaps it is greater than 0. So in this video now we're going to use that concept to explore a particular problem that will help us to gain insight into the function of an exponential order. Thank you. So for the exponential order, we're going to consider two things now. The first thing is this: let's remind ourselves of the expression which says that the absolute value of f of t is less than or equals to m, then exponential gamma of t. The condition is that both m and gamma, they must be a constant. In fact, they must be positive integers. But take note, m can never be 0, of course, because we are going to use this expression to obtain the boundedness of the function f of t. Yes, so if we are going to use it to obtain the boundedness of m of function f of t, definitely m can never be 0. It must cover a particular interval. I mean, the function must have a lower band and the upper band within a particular interval. So that is the reason why constant m can never be 0. But we can have gamma, which is the order of the exponential, to be 0. So we have to consider this function f of t, which is equals to exponential 2t. This function, we have to do two things about it. The first thing now is this particular function, exponential 2t, does it satisfy the exponential order condition? Does it? Secondly, we would like to know if the Laplace transform of the function exponential 2t exists, and why or why not it exists or it does not exist. We've been talking about this expression: absolute value of f of t must be less than or equals to m exponential gamma of t, and so far the only two things we've talked about this function is the fact about this expression is the fact that m must be a constant that is greater than 0. Gamma must also be a constant that can be 0, and it must also be greater than 0. Now the third thing I want to call your attention to the fact that this expression holds when t is also 0 or t is greater than 0. Why do we even need this expression? We need it for the boundedness of function f of t, because this is the condition that can let us know that the particular function f of t that we are trying to find, this Laplace transform, it's bounded. It has the lowest minimum number and it has the highest minimum number, and both lowest number and minimum, they must be finite. So that is the reason why we need this expression. But the additional condition here is the fact that t that we've been talking about, it must be greater than or perhaps it is equals to 0. Now this condition ensures that the function f of t, it does not grow faster. That is point number 1. That this f of t, it does not grow faster than exponential gamma of t. So we are trying to use this exponential gamma of t to be a measure so that we can know how fast the function f of t is growing as t is growing large. So as t is becoming a big value, what is happening to f of t with respect to exponential gamma of t? Because that is the only condition that can let us know if the integral of the Laplace transform will converge. That's the point. Because once we are very sure that the function f of t is growing lower than exponential gamma of t, definitely there will be a Laplace transform. So we can now consider our problem now, which is f of t is equal to exponential 2t. So the absolute value of f of t is exponential 2t, which is our function. And if you look at this very well, you will notice that no matter what constant of m and gamma that are chosen, the absolute value of f of t will grow faster than exponential gamma of t. Do you know the reason? 2 is a positive number. That is it. Look at that. 2. That 2 is a positive number. You know, we are talking about exponential 2t. And that 2 is a positive number, which will be growing larger. So as t is increasing, something will be happen to exponential 2t. I think we have to plot this graph to see how it behaves. Yes, of course. Or perhaps we should plot the... Okay, no, that may not be really possible. But one thing we are very sure is that any value of gamma you use, you will notice that exponential 2t will grow faster than exponential gamma of t, of course. So for any finite gamma. So this is an indicator that this function we are talking about, which is exponential 2t, that we want to find is Laplace transform, it does not satisfy the exponential order condition. If you still don't get this point, let's go back to our lecture note. Look at the page 2 and 3 of our lecture note. Oh no, page 1. That is page 1 of our lecture note. You will use this. You can still use the same approach. If you go back to lecture note, you will notice that this exponential 2t too, we actually discover that exponential 2t is not a function of an exponential order, because exponential 2t will grow larger than exponential gamma t as t is growing large. So now that we have realized that there may be a kind of issue with exponential 2t, so let's take a step further to find its Laplace transform. You know, as you can see on the screen now, we evaluate the integral from 0 to infinity, then exponential minus st multiplied by that f of t. And in this case, that f of t is exponential 2t. So if you join this together and you factorize t, what we have is 2 minus x multiplied by t. But for this integral to converge, the term, which is exponential 2 minus x multiplied by t, it must decay. You know, see, if you want to get this very well, you can pick your phone to plot the graph of exponential plus t. Then also plot the graph of exponential minus t. Compare the two together. You will see that minus t, it will decay. But that of plus t, it will diverge. You know, the value will be growing so large. So for us to capture this now, most especially this particular integral, the power, which is 2 minus x, it must be a number that will be negative, so that if 2 minus x is negative and negative is multiplied by t, then the exponential will decay over the interval of 0 and infinity. Or in other words, I can say that as the interval is growing to a large number, the function will be decreasing. So if you look at this very well again now, you will now see that the most important condition we need here is that 2 minus x, it must be a negative value. That is why you can see now that for this particular function to converge, or let me say it, for this integral to converge, or let me say it this way, for the Laplace transform to exist, the term, which is exponential 2 minus x multiplied by t, it must be decreasing. It must decay as t is growing to a large number. And when can we get this done? That is if 2 minus s is less than 0. You know, anything less than 0 is what? Negative. So if 2 minus s is less than 0, then we can resolve this particular inequality. Because from this inequality now, 2 can go to the other side. Then by the time you multiply or you divide both sides by negative value, the inequality will change. So what we're now trying to say is that provided x is greater than 2, if x is greater than 2, now let's go back to that expression. If x is greater than 2, that will be 2.1, right? Now 2.1, 2 minus 2.1, what would it give us? It will give us minus 0.1, and that minus 0.1 multiplied by t, it will make the function to decay. So this Laplace transform of exponential 2t, it may exist under the condition that x must be greater than 2. Because if x is greater than 2, that means that, for instance, it's 2.2. So let's go back to the last integral now. That will be 2 minus 2.2. So 2 minus 2.2 will give us minus 0.2, which means that what we are trying to evaluate is integral from 0 to infinity exponential minus 0.2 times t. and because of that negative value, it will decay. I will still ask you this question again. Please plot the graph of exponential 5t. Also plot the graph of exponential minus 5t. What did you discover? You will see that the case of exponential 5t, the function will be growing so large, and that will make it to diverge. But if you plot the graph of exponential minus 5t, the function will be decaying. So that is an assurance that the integral will exist. So what we are now trying to say now is this, that if x is less than or equals to 2, which is the opposite of what I've said earlier, that x is greater than 2. So if you consider x less than or equals to 2, then you now notice that exponential 2 minus x multiplied by t, it will grow unbounded. It definitely grows unbounded, and as t tends to infinity, so which causing the integral to diverge. So the function, which is exponential 2t, it does not satisfy the exponential order condition because it grows faster than any exponential of the form exponential gamma of c. So what we can now deduce from this is that the Laplace transform of that function f of t, which is equals to exponential 2t, it does not exist unless x is greater than 2. So what we are not trying to say is that the function exponential 2t, it has a Laplace transform, but this Laplace transform only exists if x is greater than 2. But if x is less than or equals to 2, there will be problem, because if x is less than or equals to 2, then the exponential 2 minus x will diverge, it will become unbounded. So this one will now help us to realize that it's not all functions that can have the Laplace transform. Even some may have the Laplace transform under a particular region of x interval. My dear wonderful students, so at this stage we can actually summarize the whole thing. And the summary is very simple. The summary we can just say is the fact that the function exponential 2t does not satisfy the exponential order condition. Because that would be true if the order gamma is 0 or is greater than 0. Let me say it again. When the exponential order gamma is 0 or perhaps is greater than 0, exponential 2t will not satisfy the exponential order condition because it grows faster than any exponential of the form. Because don't forget the exponential gamma t, it's when gamma is 0, we have exponential 0t, and exponential 0 is what is 1. So when gamma is 1, when gamma is 2, when gamma is 3, when gamma is any other of that exponential, we will definitely discover that what we see on the screen is true, because the function exponential 2t will not satisfy the exponential order condition. So definitely, I can just say that the Laplace transform of f of t does not exist unless s is greater than 2, which imposes a restriction on the domain of x. So if we are to look at this better, so I'll just say it this way, that Laplace transform of exponential 2t is equals to the integral 0 to infinity exponential minus st multiplied by exponential 2t dt. This thing will exist if and only if s is greater than 2. But if x is less than 2, the Laplace transform does not exist because the integral will diverge. Thank you very much for watching this video. Thank you. So see you again. Bye.